Hi there, Miss Barber here. This lesson is titled The Law of Large Numbers. The learning objectives for this lesson are: understand and apply the law of large numbers, and calculate and interpret expected values. The law of large numbers. The law of large numbers applies to a process for which the probability of an event A is P of A and the results of repeated trials are independent. If the process is repeated through many trials, the proportion of the trials in which event A occurs will be close to the probability P of A. The larger the number of trials, the closer the proportion should be to P of A. Let's consider. We illustrate the law of large numbers with a die rolling experiment. The following figure shows the results of a computer simulation of rolling a die. Along the horizontal, the title is the number of rolls, and the units increase by 500, starting at 500 and going all the way to 5,000. Vertically, it is the proportion of ones that are rolled. The units marked are 0.1, 0.15, and 0.2. Let's observe that as we increase the number of rolls, the proportion of ones gets closer and closer to 1/6, which is the theoretical probability. Example, roulette. A roulette wheel has 38 numbers, 18 black numbers, 18 red numbers, and the numbers 0 and 00 in green. Assume that all possible outcomes, that is, the 38 numbers, have equal probability. A. What is the probability of getting a red number on any spin? Solution. The probability of red is equal to the number of ways red can occur divided by the total number of outcomes. That would be equal to 18, that's the number of red numbers, divided by 38, which is the total number of numbers. That is approximately 0.474. Part B. If patrons in a casino spin the wheel 100,000 times, about how many times will a red number be the outcome? Solution. The law of large numbers tells us that as the game is played more and more times, the proportion of times that the wheel shows a red number should get closer to 0.474. In 100,000 tries, the wheel should come up red close to 47.4% of the time, or about 47,400 times. Expected value. Consider two events, each with its own value and probability. We compute expected value as the product of the event 1 value times the event 1 probability plus the product of the event 2 value times the event 2 probability. This formula can be extended to any number of events by including more terms in the sum. The notation E of x equals, the big Greek sigma is read as the sum or summation of x, which is the event value, times P of x, which is the probability of that event. Example, insurance. Suppose an automobile insurance company sells an insurance policy with an annual premium of $200. Based on data from past claims, the company has calculated the following probabilities. An average of 1 in 50 policyholders will file a claim of $2,000. An average of 1 in 20 policyholders will file a claim of $1,000. And an average of 1 in 10 policyholders will file a claim of $500. Assume that the policyholder could file any of the claims above. What is the expected value to the company for each policy sold? Solution. Let the $200 premium be positive. That is, it's their income with a probability of 1, since there will be no policy without receipt of the premium. The insurance claims will be negative. These are the expenses. So, E of x is equal to 200 times 1 minus 2,000, which is the value, times 1/50th, the probability that corresponds to a claim of 2,000, minus 1,000 times 1/20th, minus 500 times 1/10. Computing the arithmetic, we get that the expected value is $60. This suggests that if the company sells many policies, then the return per policy on average is $60. The gambler's fallacy. The gambler's fallacy is the mistaken belief that a streak of bad luck makes a person due for a streak of good luck. Think about this. We have streaks. For tossing a coin 6 times, the outcomes HTT, HTH, and HHH, HHH, or all heads, are equally likely. Example, continued losses. Suppose you're playing a coin toss game in which you win $1 for heads and lose $1 for tails. After 100 tosses, you are $10 in the hole because you flip perhaps 45 heads and 55 tails. So you keep playing the game. You continue playing until you've tossed the coin 1,000 times, at which point you've gotten 480 heads and 520 tails. Does the result agree with the law of large numbers? Have you gained back any of your losses? Explain. Analysis. The proportion of heads in your first 100 tosses was 45%. After 1,000 tosses, the proportion of heads has increased to 480 out of 1,000, or 48%. This agrees with the law of large numbers because the proportion grew closer to 50%. However, after 1,000 tosses, you've won $480 for the 480 heads while losing $520 for the 520 tails, for a net loss of $40. In other words, your losses have actually increased from $10 to $40 despite the fact that the proportion of heads grew closer to 50%. Example, planning for rain. A farmer knows that at this time of year in his part of the country, the probability of rain on a given day is 0.5. It hasn't rained in 10 days, and he needs to decide whether to start irrigating. Is he justified in postponing irrigation because his region is due for a rainy day? Analysis. The 10-day dry spell is unexpected, and like a gambler, the farmer is having a losing streak. However, if we assume that weather events are independent from one day to the next, which is often but not always the case, then the probability of rain is still 0.5 on any given day, so the region is not due for rain. The house edge. Gambling houses or casinos generally have games set up so that the house always has a higher probability of winning than patrons. For any particular game, the house edge is the expected value to the house of each individual bet. Here's an illustration of house edge with roulette. The roulette wheel pays even money on a bet of red, but the probability of winning, which is P of red, is 18/38, or approximately 0.474. Since the probability of winning is less than 50% and the game pays even money, the house has an edge on this type of wager.